In Chapter 15, we conclude our study of the ocean, looking at waves and wave action and tides, as well as currents. So when we look at the circulation and the movement of water across the ocean surface, we're going to define what some of these are. So currents are masses of water that flow from one place to another, and we can track the movements of these. Most of the surface circulation of the ocean is due to winds that blow across the surface. And so we get these huge, slowly moving currents and circles that we see out in the open sea and along the coastline. So we'll watch a smart figure, a couple of smart figures actually, one about the Gulf Stream, which is really probably the most studied surface current in the oceans. And then we'll watch another one about some of the other major surface currents.
Located off the east coast of the United States is one of the world's most powerful current systems, the Gulf Stream. It distributes a large amount of warm water from the Gulf of Mexico and Caribbean Sea northward to the North Atlantic Ocean. Data from Earth-orbiting satellites equipped with advanced, very high-resolution radiometers can be used to determine sea surface temperatures. In this false color image, red and orange colors indicate warm ocean water, while blue and purple indicate colder water. The Gulf Stream is visible as a sinuous band of red, wrapping around the southern tip of Florida, moving up the eastern seaboard, where it changes color to yellow and then flows into the waters of the North Atlantic Ocean. The position of the Gulf Stream varies once it passes Cape Hatteras, North Carolina. In this simplified map view, the Gulf Stream can be seen changing its position and wiggling around in a snake-like fashion. These fluctuations create curving loops of water known as meanders, similar to those seen in the shapes of streams on land. The ocean transfers heat in a similar fashion as our atmosphere through something akin to storms. These ocean storms are known as eddies. The Gulf Stream produces eddies that spin off of the primary current path and move heat outward. Eddies can either have a cold core, where the water at its center is cold, or a warm core, where there is warm water at its center. Eddies are formed when rings are pinched off as the Gulf Stream meanders. The direction that the eddy pinches off determines whether it has a cold core or a warm core. If the eddy pinches off into the warm water to the south, cold water is captured at its core. On the other hand, if the eddy pinches off into the colder water to the north, it captures warm water at its core. These eddies sometimes last for several months, providing a unique ecosystem for marine life. Eventually, the eddies dissipate into the surrounding water, or in some cases, they rejoin the Gulf Stream. The Gulf Stream moves an impressive amount of water and heat into the northern latitudes. As it does so, it directly affects weather and climate patterns over the entire globe.
Hello, this is Callan Bentley. Welcome back for another Smart Figure. After watching this video, you should be able to describe what a gyre is and how many gyres can be found in the world ocean. Let's begin by taking a look at this picture. This is the west coast of Namibia in Southwest Africa. And you can see here chlorophyll. This has been spotted by a satellite. So the chlorophyll concentration shown down on the bottom is basically greater if you have a warm color like orange or red, and less if you have a cold color like blue. There's definitely some plankton that are having a good time here. They are photosynthesizing, which is increasing the chlorophyll concentration. But that's not really why we're looking at this picture right now. What we're looking at is that this chlorophyll is getting dragged off in strands, and these strands are basically being pulled off in a northwestward direction. So something's moving these strands of chlorophyll, these chlorophyll-rich waters, in that direction. If we take a look at this map, we'll get a sense of what that is. You can look there at that same spot in the smack dab middle of this map, and you can see near Walfish Bay, Namibia, that there's a current there, and that current is responsible for moving that chlorophyll up into the northwest. You can see that there are other currents, all of them cold here on this map, moving around the world ocean. There are also currents that are warm, so if we switch and look at those instead, we see a different pattern. When we put the warm and the cold together, we see a pattern emerge, and that pattern is that in each of these oceans we have this sort of spiral-shaped current. So there's one in the Indian Ocean, there's one in the South Atlantic, one in the North Atlantic, there's one in the North Pacific, and there's one in the South Pacific. Each of these large circular patterns is referred to as a gyre. Notice that the gyres flow clockwise in the northern hemisphere and counterclockwise in the southern hemisphere.
So as he's talking about these gyres and the direction that they flow, this is due to what we refer to as the Coriolis Effect, and this is due to Earth's rotation. This really affects weather patterns, and so we'll get to the Coriolis Effect and actually do an experiment with the Coriolis Effect when we get to chapter 18 as we're talking about weather patterns.
These gyres have many consequences. So here's an example. This is looking at temperature on both the east coast and the west coast of South America. So two cities are chosen, Rio de Janeiro, which is over on the east coast, and Atacama, which is over on the west coast. You can see that Rio is just a little bit south of Atacama, but Rio has the higher temperatures. So overall, the temperatures for Rio de Janeiro are much higher than the overall temperatures for Atacama. And that's because of the influence of these currents. The Brazil current basically brings heat down from the equator past Rio, whereas the Peru current is bringing colder waters up the coast past Atacama. Now, that's temperature, but what do you think would happen in terms of precipitation in these two different regions? Well, hopefully you had a second to think about it. You remember that warm air rises. With the Peru current bringing all that cold water up past the Andes Mountains, the air above that water is also cold, and so it has very little incentive to rise and flow over the Andes to generate rain. And as a result, you end up seeing that there's actually an extremely dry desert there, the Atacama Desert. And that Atacama Desert is one of the driest deserts in the world. So you can see there's not a plant to be spotted anywhere in this photograph, and that's because of the influence of the Peru current on the coast of South America. The same thing, in fact, is true in Namibia, where we started this smart figure. Thanks very much for your attention. This has been another smart figure.
So in those videos, we got a look at the major surface ocean currents. So now we're going to take a look at two other processes that affect currents. And these are going to be vertical movement. So kind of this up and down movement as opposed to the horizontal movement like we were just looking at. So we have upwelling and then deep ocean circulation. So we're going to watch two more smart figures that explain upwelling and the deep ocean circulation.
Hi there, this is Callan Bentley. Welcome back for another smart figure. After watching this video, you should be able to describe how winds trigger coastal upwelling and what the effect is for life. This is a satellite view of the coast of southern Africa. So we've got South Africa, Namibia, and Angola. And along the coasts of those countries, you can see that in the ocean there is plankton. That plankton is photosynthesizing. And where there's the greatest proportion of plankton, there's the most photosynthesis and hence the most chlorophyll. So chlorophyll is that green molecule in plant that helps the plants capture the sun's energy and use that energy to suture together carbon dioxide molecules and water molecules, making simple sugars that the plankton can use to grow and reproduce and do all the things that plankton do. So where there's a lot of chlorophyll in the water, there's a lot of plankton. Those are these sort of red colors. Where there's very little chlorophyll, very little biological activity, it's the sort of cooler colors, the blues. And you can see here that there are these sort of filamentous strands that almost look kind of like flames going off the coast here. And those flames are going off in sort of a northwestern direction. So what's up with that? Well, the area we were just looking at is shown in the little red box here. And you can see that the winds here blow more or less parallel to the coastline. Now, because of the Coriolis effect in the southern hemisphere, there's a deflection towards the left. So the surface currents that are generated by those winds aren't actually parallel to the winds. They're a little bit left of the direction the wind is blowing. So you get this surface current, which is basically pulling away from the coast at this location. If you look at a cross-section through the area, it might look something like this. You've got these winds that are essentially pushing material offshore, and then that causes new water to move up to replace the water that's being blown offshore. The water that's coming up from depth has all kinds of nutrients dissolved in it that are less common in surface waters. And so those nutrients can actually fertilize the water for the plankton that are there. They are the limiting nutrient for those plankton. So the plankton basically take advantage of all that good food and they start to grow and reproduce. And so you get one of those big chlorophyll-rich patches. As the wind continues to blow and the current continues to flow away from the shore, those plankton are dragged along with it and they end up going offshore too. So that explains why we have this tremendous concentration of chlorophyll all along the coast here, but it also explains these neat little filaments that go off in sort of a northwesterly direction. Those are basically showing us what direction the current is flowing at this location. Thanks very much for your attention. This has been another Smart Figure.
In addition to the surface currents, there is also a general flow of water in a deep ocean conveyor belt circulation. A shallow current of relatively warm water slowly moves from the Pacific Ocean through the Indian Ocean and into the North Atlantic. In the North Atlantic, this shallow current cools and sinks. A cold, deep current then flows south out of the Atlantic Ocean, where it joins the flow of deep water near Antarctica.
So part of this, as we look at this kind of conveyor belt that you see here between the shallow currents and the deep currents, has to do with the density differences among the two. Denser water is going to sink and then spread out beneath the surface. The density differences are due to temperature and salinity, like we talked about in the last chapter. So the deep ocean circulation is also referred to as a thermo-haline circulation. Thermo referring to heat, haline referring to salt. So the increase in density can be caused by, as we saw again in the last chapter, a decrease in temperature or an increase in salinity. The water you see there that starts to sink is up around the Arctic Circle, very high northern or very low northern latitudes. And as we look at that, you see how the water sinks because it's becoming colder. So the temperature is dropping. Salinity also is increasing because of the sea ice that's forming. So when the sea ice forms, it's primarily formed from just water. The salt doesn't actually freeze, and as a result, the water there becomes or has a higher salinity amount. So you have this water that's colder, it's saltier, contains, a higher salinity, and so it's going to sink. And then you see there kind of come around down through the coast of Antarctica.
Some of this deep water eventually flows north back into the Indian and Pacific Oceans, where it rises into the shallow warm current.
So now that we've taken a look at the ocean currents and their interaction, now we're going to take a look at the shoreline. So the shoreline is considered a dynamic interface. Dynamic because it's always changing. The shoreline is never the same due to the effect of waves, sea level fluctuations, climate, topography, and it's considered an interface because it's a boundary where different parts of a system interact. And at the shoreline, we have the air, land, and sea all coming together. The other thing that's interesting about shorelines is that they vary greatly from place to place. The shoreline on the Atlantic East Coast is not the same as the shoreline on the Gulf of Mexico or the shoreline along the Pacific Ocean. So the coastal zone changes rapidly. It's constantly modified by waves. We have the crashing surf that will erode the land. And when we look at present day shorelines, they're not just the result of wave action. They're the result of other geological processes. Number one being the rise in sea level that accompanied the close of the Pleistocene epoch when we came out of the last or the most recent ice age. We also have stream erosion, glaciation, volcanic activity, and the forces of mountain building that can affect the shoreline. And of course, we can't forget human activity. Human activity has greatly altered the shoreline, and we'll discuss more about that a little bit later. So you see this figure, this is on page 458 in your book. And so you see a lot of terminology associated with this coastal zone. So now I'm going to take some time and go through each one of these, kind of talking about them. So we have shore, shoreline, coastal zone, and coast. And we use these a lot, and often we may use them interchangeably, but they're not really the same thing. So the shoreline you see here marked by the edge of the water and sand. So shoreline is the contact between land and sea. Okay, so the shoreline is the contact between land and sea. And this is going to migrate throughout the day as we get low tide and high tide. And so you can see here, we've got kind of this dotted line here where we have the low tide shoreline. And then this line up here, that's where we've got a little bit darker sand. That's the high tide shoreline. And we'll talk about tides later on in the chapter. But as the tides come in for high tide and go out for low tide, the position of the shoreline is going to change. The shore, you see here, is the area that's between the lowest tide level and the highest elevation on land that is affected by waves. So we've got from the low tide area all the way up to what we refer to as the coastline, which is as far as the waves will come in. So even during storms, even when we have, crashing waves or high surf, the coastline marks that area. And so everything between low tide shoreline and the coastline are considered the shore. Now the coastline's not always obvious, okay? Landward beyond the coastline is referred to as the coast. And so this is where we start to see more dunes and vegetation, because this area here is not going to be affected by waves. So even though the coastline isn't always obvious, we may not see this, line marked in the sand or rocks or whatever the beach may be made up of, we will start to see, dunes and vegetation that help us identify the coast. Now, if we look at the shore area here, the foreshore, okay, so this little piece here is the area that's going to be exposed when the tide is out or when the low tide is out and high tide is in. So basically, the foreshore is the area between the low tide shoreline and the high tide shoreline. And then the back shore is from the high tide shoreline all the way up to the coastline. We also have the near shore and the offshore. The near shore is the area between the low tide shoreline and then the kind of the line where the waves are going to break, where we've still got water here, but it's along that slope there, and then offshore is everything seaward past that point. Now, if we also kind of keep this figure here and look at beaches, a beach geologically is the area where there's an accumulation of sediment found along the land margin of either a lake or an ocean. And what we'll see on beaches are these berms. So you see this kind of marking right across here that's called a berm. These are relatively flat platforms composed of sand and really kind of marked by a change in slope. And you can see this little bit of change of slope right here. And then another part of the beach is the beach face, where we start to get that really sloping surface that's going to be covered by water. Now, typically we think of beaches, we think of sand, and that is the case. Most beaches are made up of quartz grains that have been ground into sand, but in other areas, different minerals may be present. For example, we have, especially you see these in Hawaii, we have the weathered grains of basalt. So sometimes these are referred to as black sand beaches because they're remnants of the volcanic activity. In Florida, there's a picture in your book on page 458 of Sanibel Island, which is covered with shells. And so the sand there is made up not only of quartz, but also of whole shells, pieces of shells, and the remains of organisms that have died. So the biggest part of this chapter that we're going to get into now we're going to look at ocean waves. So we've looked at currents, and currents and waves are not the same thing. Currents are surface. They are controlled, as you learned, by in part wind, but mostly by looking at the upwelling and the difference in temperature and salinity and overall wind motion. Ocean waves also derive their motion from wind, but ocean waves are energy, okay? They are energy traveling along the interface between ocean and atmosphere. So as the wind blows and it comes across the surface of the ocean, it basically transmits its energy from wind, from the atmosphere, into the water in the ocean. So when you see waves, what you're seeing is energy. Okay, so you're physically able to observe energy when you look at waves. Wind-generated waves provide most of the energy that is going to shape and modify shorelines. Now, if we look at this image here, this is on page 459 in your textbook, you see the different parts of the waves. So the highest point, or the top of the wave, is referred to as the crest. And then the lowest point is referred to as the trough. So as the wave is moving this way, you see from left to right, we have varying crests and troughs. Halfway between the crest and the trough is the still water level. So if the water was still, the still water height is what it would be. The vertical distance between the trough and the crest is referred to as the wave height. Okay, and then the horizontal distance between the crest and the next crest, or between trough and trough, is referred to as the wave length. So wave height is the vertical distance. Wave length is the horizontal distance. The time it takes one full wave, so a wavelength, the time it takes for one wave to pass a particular position is called the wave period. Now, the wave height, the wave length, and the wave period are all determined by three factors. The wind speed, so how fast is the wind blowing? The length of time that the wind has blown, so the duration, and fetch. Fetch is the distance that the wind has traveled across open water. So we've got how fast it's blowing, how long it's been blowing, and then the distance it's traveled across open water. As the quantity of energy that's transferred from the wind to the water increases, the height and steepness of the waves increase. And eventually we get to a critical point where the waves get so large they topple over, and that's referred to as a white cap. And you can see some white caps at the top of page 460. So now we're going to watch another smart figure video that looks at how the movement of water particles is different than what we actually observe in the wave.
Hi there, this is Callan Bentley. Welcome back for another smart figure. After watching this video, you should be able to describe the nature of the motion of waves that we see in the ocean or on other bodies of water. Have you ever wondered why curling waves break? Why surfers ride waves in some places but not in other places? Well, it has to do with the way that waves move. Waves are basically the transmission of energy through a medium, and the medium in this case is water. They travel along the surface of the water, and the waves are bigger basically when there's more of a distance over which the wind blows, a so-called fetch. But the water itself is moving in a very different way than the waves are. So the actual water is moving in a little path that is basically circular. So if you follow a single little particle of water, it tends to make a circular path. And if you go deeper in the water, that same circular path exists, except the circle is smaller. And at a certain depth, you basically don't see any more motion at all. And that depth is basically about half the wavelength, where the wavelength is the distance from one wave crest to the next, or from one wave trough to the next. All right, that wavelength, if you take half of it, sort of swivel that around into the depth there, like that, you'll find that there's very little wave motion below about 1/2 of the wavelength. So you can visualize this with a boat floating in the water. As a wave approaches that boat, it basically goes underneath the boat. The boat kind of slides up the oncoming face of the wave, rides across the top of the wave as it passes underneath the boat, and then slides down the back face of the wave as the wave continues off towards the right. And at the end of this, the boat is still in its same position, but the energy of the wave has been transmitted through that area. Now this ends up affecting the scene that we see at the beach when we have shallow water. And basically if the water is shallower than that wave base, 1/2 of the wavelength deep, then the waves start to feel bottom. And that means that those little circles down there at the bottom, the little particles of water, are starting to find their path impeded by the sediment on the bottom of the ocean. As a result, there's frictional drag there, and the particles are moving a little bit slower at the bottom of that stack than they are at the top of the stack. So if the top of the stack is moving further than the bottom of the stack, the whole thing basically starts to tip over. And so you end up getting that classic curling shape of breakers. So if you were a surfer, would you want to be in the really deep water, or would you want to be in water which had a depth which was less than 1/2 of the wavelength? Well, if you are a surfer and you hang out here, you're not going to be catching very many waves because the waves are not going to be very tall and they're not going to be curling over into breakers. So you want to be somewhere close to where those waves are breaking, and hopefully that's big waves over relatively shallow water. Thanks very much for your attention. This has been another Smart Figure.
So there we saw basically how waves work and how they're able to transfer energy. And so now we're going to look at the work of waves and how they can cause erosion and deposition. So wave erosion can be caused by several different things. Number one, the wave impact. Along most coasts, waves are going to break along the shoreline about 10,000 times per day. So all of that is going to have an impact on what's happening at the shoreline. Each wave can hurl thousands of tons of water against the land. Your book mentions that in the wintertime, when Atlantic waves are stronger, the pressure exerted averages nearly 10,000 kilograms per square meter, which is 2,000 pounds per square foot. And if we're talking about storms, then that pressure is even greater. Like right now, this past week, there's been a huge nor'easter storm that's been impacting New Jersey, New York, Maine, and the coastline up in that area. A nor'easter is very similar to a hurricane, except it doesn't form over tropical waters. And so they have seen a lot of coastal flooding and erosion that's taking place because of the strength of these waves that are slamming into the coast. So as waves come in, this breaks down rock material, which does help supply sand to beaches. We also get the work of abrasion, which is the sawing and grinding action of the water armed with rock fragments. So when we look at waves, it's not just water that's being hurled against the shore. There's also, sediment that's embedded in this water. And as the water with all of this sediment in it comes up, it abrades what is there, because you think not all of our shorelines and coastal areas are composed of sand. Some of them have, rocks or cliffs, and the sediment that is trapped within these waves is going to abrade those rock facings. So there are really several different types of movements that can occur with wave action. So we have movement that is perpendicular to the shoreline. Let me go back one. And we can have wave refraction, and then we have movement that's parallel to the shoreline. So if we look at movement that is perpendicular to the shoreline, we have swash and backwash. So just to kind of define what those are, swash is the water from the collapsing breaker. So as the water kind of comes up in the surf, and then as it flows back downward, that's called the backwash. Okay, so we have swash as it's coming up onto shore and backwash as it's leaving the shore. So swash and backwash are going to move sand up onto the beach face and then back away from the shoreline. Whether there's a net loss or gain of sand depends on the level of wave activity. When there's less energy in the waves, then as the swash comes up, it kind of soaks into the beach, and that lessens the backwash. But if there's more energy in the waves, like from a storm or from strong winds, the beach is already saturated, so less of the swash soaks in, so the backwash is going to be stronger, and it's going to carry sand back away. So the second type of movement that we get is wave refraction, and refraction refers to bending. And this can happen with an ocean wave, it can happen with a light wave. The wave is going to arrive parallel to shore. So we're going to see a smart figure on how wave refraction can affect the sand deposition.
Hello, this is Callan Bentley. Welcome back for another smart figure. After watching this video, you should be able to describe what wave refraction is, how it happens, and what consequences it has for the shoreline. You'll recall from another smart figure, or from reading in your textbook, that waves tend to break at the beach because the waves feel bottom. In deeper water, wave particle motion is limited to a depth that is about 1/2 the wavelength of the waves. However, over shallower water, the waves feel bottom, which means basically there's wave particle motion that wants, quote unquote, to be at a greater depth than the bottom of the water. And as a consequence, there is frictional drag there, the waves tend to pile up higher, and they tend to tip over as the top of the wave moves faster than the bottom of the wave. That same principle of waves feeling bottom is the reason that we see wave refraction. So here, we're looking at a situation where we've got a rocky headland and cove sort of on either side. As waves approach that area, they find shallower water immediately offshore of the headland, and so they slow down. However, there's still deep water offshore of the two cove areas, so the waves move full speed ahead in those areas. As part of the wave is going faster than another part, the wave curves into a new shape. And we can see this in this photograph here. You can see that offshore, the waves are coming in basically kind of like that. And then as they start to feel shallow water over in this area immediately offshore, they slow down. And the waves out here in the deeper water, let's just go ahead and write the word deep there, those waves are still moving at full speed. And so the waves tend to sort of curve around as they go past this little point of land. And so by the time that the waves make it to the beach over here in the foreground by where the cars are, you can see they're in a totally different orientation. So this orientation here is basically an orientation that's parallel to the shore, whereas the original orientation off at sea was quite different indeed. Okay, so here's another example of this where we actually have a rocky headland and we see the wave fronts coming in. The red arrows show the wave path. You'll notice that there are basically big boulders exposed right here offshore of the headland, whereas right here there are sand deposits, and that's of course true over in this area as well. So my question for you is, why do we see different sedimentary particle sizes in these three different areas? Okay, you've had a moment to think about it. Hopefully what you came up with is that the wave energy is really concentrated right here on the headland. So there's a huge amount of wave energy there. Any sand that's produced in that area is quickly going to get stripped away. Whereas in these areas, like right here and right here, the wave energy is dissipated. You can see those arrows spreading out, and there's more space between the arrows. As a result, the water energy is lowered, and it's no longer capable of moving that sediment. Instead, it ends up dropping it out and depositing it. I'll bet you figured that out just fine. Congratulations, and thanks for your attention.
So another type of movement that we can get is the movement that is parallel to shore. And so we're going to see another smart figure video that discusses longshore currents, which are able to contribute to what we refer to as beach drift, which is where the sediment is transported more in a zigzag pattern along the beach face instead of just a straight pattern that we see with the swash and backwash.
Hello, this is Callan Bentley. Welcome back for yet another smart figure. After watching this video, you should be able to describe what longshore currents are and why they occur and how they affect the shoreline. So take a look at this picture. Something funny is going on here. You can see that the shoreline here has sort of a sawtooth shape. That sawtooth shape is a consequence of both a natural phenomenon, a longshore current, and human intervention. So the idea behind a longshore current is this. Waves generally approach the shore at a slight angle. Even though they're bent towards parallel by the effects of wave refraction, waves hit at a slight angle and they tend to push sand grains up the beach at a slight angle. However, when the waves drain back down, they drain downhill, so it's a different direction. So the waves come in, they push the sand grains up the beach at an angle, draining back downhill, in at an angle, out downhill, in at an angle, out downhill. So overall, we've got this drift, which at the beach is parallel to the shore. You may have experienced this. If you've ever gone swimming at the beach and you wade in one area, play in the waves for a while, and you come out, you might find that you've been washed down shore to a new location. The same thing is happening at depth. So within the reach of the wave base, sedimentary particles they're moving in at an angle and down towards deeper water, and that zigzag path basically parallels the beach drift, and we call that the Longshore Current. So the Longshore Current is the net transport of the sediment along the beach in one direction or another. In the inset photograph down in the lower right, you can see that the waves are approaching the beach from the lower left, and so they'd be pushing sedimentary grains up the beach towards the right. This can end up affecting the shoreline.
So we're going to pause there and come back here in just a few minutes and discuss these features that can result from wave erosion and wave deposition. So another process that we can see at the shoreline is referred to as a rip current, or sometimes these are referred to as rip tides, which is really a misnomer because they have nothing to do with tides. But rip currents are concentrated movements of water that flow in the opposite direction of breaking waves. Most of the backwash is going to find its way to the ocean as what we refer to as a sheet flow, but sometimes the portion of returning water is going to move seaward in the form of this rip current. They don't travel far beyond the surf zone before they're breaking up, and you can see these. You can see how this kind of middle of the picture here, you don't see waves that are coming in. This is a rip current. So this water is going out here and interfering with the way that sediment is coming up. And so these can be dangerous to swimmers because they can be carried far away from shore. So the best thing to do is try to swim parallel to the shore until you get out of the rip current, and then let the surf kind of bring you on in. So with all of this action that's taking place on the shoreline due to waves, and particularly these longshore transport processes that we learned about, we get some features that occur. There are interactions among, of course, the water and the shore, and the importance of these depends on some features or some factors that are local to each area of the shoreline. These can include the proximity of the coast to a river, and particularly if that river is filled with sediment. What is the degree of tectonic activity that's happening in the area? What is the topography and composition of the land? What are the prevailing winds doing? What is the weather pattern that exists in the area? And then how is the shoreline, how is the coastline configured? So most shorelines are subject to erosional and depositional features. So we can see both. We can see erosional features and depositional features depending on where we are, depending on these local factors that I just mentioned. Many coastal landforms are due to erosional processes, and we're going to look at a couple of these. So what we see here is a wave cut platform and a marine terrace. So a wave cut cliff originates due to the surf against the base of the coastal land. As this wave erosion continues, the rocks that are overhanging that notch crumble into the surf. The cliff is going to retreat, and we get this wave cut platform. Okay. this is what is left behind by the receding cliff. If the wave cut platform is uplifted due to tectonic activity, then we can get this marine terrace that results. Okay. Another feature that we can get, you see two of them here, a sea arch and a sea stack. Because of refraction, as you learned, the waves will attack headlands. As the surf attacks those headlands, it erodes the rocks selectively, wearing away the softer or more highly fractured rock faster than the harder or not as fractured rock. So we can get sea caves that form, and as erosion continues, we can get this sea arch that forms. Eventually this arch here in the middle will break and we're left with these sea stacks. So these originally were arches. So there was originally rock that connected these two and these two, but they caved in, they fell in. And so we're left with what's referred to as a sea stack. Now, so these are erosional features, but we can also get depositional features that are due to sediment that's transported along the shore. We'll see depositional features in areas where wave energy is lower, because we're not going to have as much energy, so we're not going to see the erosion like we do with the wave cut platform or the sea arches and the sea stacks. So now I'm going to continue that video I paused earlier and take a look at some of the depositional features.
So here you can see that we've got a fairly rough shoreline with a bay and a sea arch and an island. If a longshore current brings in sediment from the left, it can modify that shoreline. So it can end up building up a spit out across the mouth of that bay.
So let me go back just a little bit here, a little bit further. So a bay that you see here is where water has kind of cut in and eroded some of the features of the shore there. Here is a sea arch that has formed. You can see here on a headland. So this little piece right here would be a headland. And here's a little island out here. So this could be like a barrier island that has formed. And we'll talk a little bit more about those. So here are some features that are already present, and so we're going to see what can happen there.
If the longshore current brings in sediment from the left, it can modify that shoreline, so it can end up building up a spit out across the mouth of that bay, depositing a tombolo between the mainland and the island. Perhaps the sea arch collapses and we're left with a sea stack.
So here you can see a few of these features. So we have a spit, which is when sand is going to be deposited across the mouth of a bay. And usually it'll kind of have this hook shape on it. There's a picture on page 466 in your book of Cape Cod. And you can see some spits that have formed there. And in particular, the Provincetown spit. So you kind of get this hook shape that forms on it. Then we have this tombolo where sand has been deposited in between the shoreline and the island here. And this can form in what we refer to as the wave shadow of a sea stack. So here we did have a sea arch, but we got a little bit of erosion that happened there. And so now we're left with a sea stack. So we can get, depositional and erosional features happening essentially together.
And then more sediment is transported along by the longshore current. The first bay is sealed off by a baymouth bar, and then a spit builds out across the second bay.
So here, this first spit that we have here now has become a baymouth bar. So we basically got a sandbar now that has sealed off this bay from the open ocean, and a spit has now formed in this other area. We've also, due to the Longshore Current here, gotten rid of our tombolo. The island is gone now. The sea stack that we saw here, if sea levels rise, that sea stack could disappear, or it could erode completely away. And so we can get more beach deposits here where we didn't really have that before.
You see we've got basically beach deposits all the way along. This is an example of how the shoreline becomes smoothed out over time thanks to the effects of the Longshore Current.
So I'm going to pause there again, and we'll come back to this video again when we talk about some things that we can do to try to prevent beach erosion. So the last thing I want to talk about when it comes to shoreline features are barrier islands. So barrier islands are mainly seen along the Atlantic and Gulf Coast. There are about 300 of them. If we start in Maine and kind of weave our way around to Texas, most of them are 1 to 5 kilometers wide and 15 to 30 kilometers long. So they're not very big. And they have a lagoon or an area of water that separates them from the mainland. This is relatively quiet water because it's cut off from the energy that's being, transferred in ocean waves. Barrier islands can form in several different ways. One of those would be if a baymouth bar or spit were to become completely severed from the mainland. So you can already see at the north end here of Cape Cod, you can see there's starting to become a little split in there. And so if this was to become completely severed from the mainland, then it would become a barrier island, and this water in through here would be called a lagoon. Same thing here on this little spit that you can see. If this was to become severed, that could create a barrier island. So when we say we have about 300, this is evolving. The shoreline is always evolving. Barrier islands disappear and reappear based on sea level changes, based on deposition. Storms can create barrier islands or take them away, depending on whether deposition or erosion takes place. And that, when we talk about storms and turbulent waters, that's another way that we can create barrier islands. And then some were created during the last glacial period as when the sea level was lower. We got deposition of sand, but when the sea level rose, those higher dunes became separated from the mainland. Now, the next section of your chapter talks about the differences in America's coasts, and on pages 468 and 469, you have kind of this spread of pictures of some different features along the Pacific coast, the Gulf Coast, and the Atlantic coast. I would encourage you to kind of check that out. So the next thing we're going to get to is how we can stabilize the shore. So how do we protect the shore from these erosional problems? And so we can have hard stabilization, and there are several different types of hard stabilization. We have jetties, we have groins, breakwaters, and seawalls. So here is an example of a jetty that can be built basically to protect inland areas from deposition, as you kind of see here, protecting this boat dock basically. And now I'm going to go back to Smart Figure 15.17 that we've been watching, because it discusses jetties and what they do.
How would that affect this situation? Here you've got some land shown in orange, you've got the ocean in blue, and then you've got a little inlet here, which is access perhaps to a marina or some sort of a port in a protected location. To protect the inlet, 2 jetties, shown in green, have been built, but if the Longshore Current is moving along this shoreline from left to right, how would that interact with these jetties? Well, it's going to be bringing sediment in from left to right, but as that sediment hits this first jetty, it's going to tend to be deposited. And so we're going to tend to see deposition of new sediment in the up current direction from that jetty. Then the Longshore Current on the down current side of the second jetty is going to be sediment starved, and so it may actually end up eroding into the land there and carting away new sediment to be carried off towards the right. Here's a real-life example of this, as well as a drawing. You can see here there's the open ocean here in this photograph down in this area, the inlet here protecting the boats, and then we've got the jetties on either side of the inlet, and you can see how much more sediment has been built up on the left side of that jetty as compared to the right. And the right side actually even seems to have a little bite taken out of it right there. So that indicates that the Longshore Current in this photograph will be moving from the left towards the right. Thanks very much for your attention. This has been another Smart Figure.
So there you had a look at a jetty. That's one type of hard stabilization. Here in this figure, we see what we refer to as a groin field. So each one of these little lines that you see here would be referred to as a groin. And these are barriers that are built at a right angle to the beach that is trapping sand moving parallel to the shore. So basically, due to these longshore currents, can be constructed of rocks or wood, either one. So what happens though is sand would be trapped on one side, but then on the other side, the longshore current area beyond the groin is going to be sand starved. So the current erodes sand from the beach on the downstream side of the groin. And so you get this, what we refer to as a groin field now, so that it kind of stabilizes the entire shore. However, groins don't really provide a satisfactory solution to the problem. They're really just a temporary fix. Another type of hard stabilization is a breakwater. This is built parallel to the shoreline. So we can see in this second picture here our breakwater. Typically used to protect boats from the force of breaking waves. And so you kind of get this quiet water zone here. However, when this does happen, you do get sand accumulation. And so your boat anchorage eventually fills with sand, and then the downstream area is going to erode and start to retreat. And so that's what you've got here. Here is your breakwater. You get this accumulation of sand here, but then you get some erosion of the sand here. And then the last type, I don't have a picture of it in the PowerPoint, but there's one shown at the bottom of page 474, is a seawall, which armors the coast and defends property from breaking waves. It reflects the force of the waves back seaward instead of inward. But eventually the seawall is going to fail because the waves are going to batter it enough. So these protective structures are going to divert ocean energy temporarily, but over time, they're not going to be really effective at what they're trying to do, which is prevent erosion. So alternatives to hard stabilization include beach nourishment and changing land use. So in this image here, you have beach nourishment. Basically what we're doing is dredging some sand from offshore and then adding that to the beach. It's not going to be the same as what was already there. So you can kind of see this pipeline here that's kind of bringing it up, and you've got sand, pouring out of there. But it's different. It's different sizes, different composition. Again, not a permanent solution because this sand is also going to erode. It's also very expensive, can cost millions of dollars per square mile. The other option is to change the use of land. Instead of defending and rebuilding beaches, instead, coastal ecologists recommend relocating storm damaged buildings and then just letting nature reclaim the beach. You know, just stop trying to build along the shoreline, and just let nature do what it's going to do. But of course, that can be controversial. People, you know, want to rebuild, they want to defend their coastal developments. They see it as, you know, losing money if they're not allowed to build right on the coast. But with sea level rising, the impact of coastal storms is going to get worse. It's going to do more damage. It's going to continually erode the shore. So, you know, proponents of this idea want to just quit building along the shore, which seems to be a smart solution in my mind. Now, the last part we're going to get into in this chapter looks at tides. Tides are daily changes in the elevation of the ocean surface. And so as we looked, when we were looking at our diagram of the shoreline, we saw that low tide area and high tide area. And these are caused by gravitational forces on the earth due to the moon and the sun. So we're going to watch two smart figure videos that are going to explain these forces and explain the monthly tidal cycle as it correlates to the moon. And then we're going to look at daily tidal patterns. And after those two play, then I'm going to come back and talk about tidal currents, and then we'll finish up this chapter.
The monthly tidal cycle. Tides are regular, periodic changes in sea level caused by the gravitational attraction of the moon and sun, and the orbits and rotation of the Earth, moon, and sun. Gravitational attraction pulls ocean water toward the moon. Because gravitational attraction between two objects diminishes rapidly with increasing distance, there is more gravitational attraction on the side of Earth facing the moon than on the opposite side of Earth. This difference in gravitational attraction slightly elongates the shape of the global ocean, so that two bulges of ocean water develop, one on the side of Earth facing the moon and the other on the opposite side of Earth. As Earth rotates, coastlines move into and out of these bulges in the ocean, producing simultaneous high tides on opposite sides of Earth and low tides halfway between. Gravitational attraction also pulls ocean water toward the sun. The sun is much more massive than the moon, but because the moon is much closer to Earth, the moon generates larger tidal bulges than does the sun. As you can see, the moon's tidal bulges, shown in light blue, are about twice as large as those produced by the sun. In this view, you are looking down at the North Pole of Earth. Earth is rotating on its axis, and the moon is revolving around the Earth. Notice that the lunar tidal bulges remain aligned with the moon as it orbits around Earth, while the solar tidal bulges remain aligned with the sun. The red square on the surface of Earth is a reference point. When this location rotates into a tidal bulge, it experiences high tide. When it rotates out of a tidal bulge, it experiences low tide. The combination of Earth's rotation and the moon's revolution around Earth mean that most coastal areas experience 2 high tides and 2 low tides every 24 hours and 50 minutes. The tidal range, the height difference between high tide and low tide in a location, varies during the month. As the orientation of the moon to the sun changes during the month, the positions of the lunar and solar tidal bulges also change. The animation pauses after about a 1-week period. This is the time of the first quarter moon. Notice that the lunar tidal bulges and the solar tidal bulges are 90 degrees apart. This produces the smallest combined tidal bulges and therefore the lowest high tides, called neap tides. About 1 week later, at the time of the full moon, the animation pauses again. Notice that when the moon and sun are aligned, their tidal bulges overlap to produce the largest combined tidal bulges. This results in the highest high tides, called spring tides. About 1 week later, at the time of the third quarter moon, the lunar and solar tidal bulges are again 90 degrees apart, and so Earth again experiences neap tides. Finally, about 1 week later, at the time of the new moon, the lunar and solar tidal bulges again combine to produce spring tides. In all, it takes about 29.5 days to complete this tidal cycle. This time, as you view the monthly tidal cycle, you see a boat docked at the location of the red square on Earth rise and fall with the tides each day of the month. You also see a tide chart showing the change in tidal range during the month as we go from neap tide to spring tide to neap tide and finally to spring tide. This animation only illustrates the monthly tidal cycle. Other factors produce variations in tidal range during the year and differences in tides from location to location. For example, some coastal locations regularly experience relatively small tidal ranges, while others regularly experience very large tidal ranges. The greatest tidal range on Earth is found in the Bay of Fundy in eastern Canada. Tidal patterns. This animation begins with a world map showing the geographic distribution of the world's 3 different types of tidal patterns: diurnal, which is shown in yellow, semi-diurnal, which is shown in red, and mixed, also called mixed semi-diurnal, which is shown in blue. All tide graphs in this animation show a time span of 2 lunar days along the horizontal axis, and the tide height in both feet and meters along the vertical axis. The datum is the starting point for measuring tide height and is shown as a value of 0. Note that the clock above the tide graph has only an hour hand with no minute hand. The clock shows the passage of time in hours, and the graph shows the tidal conditions, alternating high and low tides, experienced at a tide recording station with this type of tidal pattern. In a diurnal tidal pattern, there is 1 high tide and 1 low tide daily. Note that the term diurnal means daily. At the end of the animation, features of the tide graph are indicated. These features include the tidal day, shown in brown shading, the tidal period, which is the time between successive high or low tides, and the tidal range, which is the vertical difference between an adjoining high and low tide. Notice that for a diurnal tidal pattern, the tidal period and the tidal day are the exact same length. In a semi-diurnal tidal pattern, there are 2 high tides and 2 low tides daily. Notice that the 2 high tides are about the same height, and that the 2 low tides are about the same height. At the end of the animation, the tidal day, tidal period, and tidal range are indicated as they were for the diurnal tide graph. Notice that for a semi-diurnal tidal pattern, the tidal period is 1/2 that of the tidal day. In a mixed tidal pattern, there are 2 high tides and 2 low tides daily. Notice that the 2 high tides are of different heights, and the 2 low tides are of different heights. This gives rise to the terminology lower low water, lower high water, higher low water, and higher high water. At the end of the animation, the tidal day, tidal period, and tidal range are once again indicated. Notice that for a mixed tidal pattern, the tidal period is 1/2 that of the tidal day. Also notice that the tidal range is measured from the higher high water to an adjoining lower low water.
your weekly activity, which I'll go over in a different video, looks at those tidal patterns that you just learned about from the Smart Figure video. The last topic here are tidal currents, which is the horizontal flow that accompanies the rise and fall of tides. These can be very important in some coastal areas. So tidal currents that advance into the coastal zone as the tide rises are referred to as flood currents. And then as the tide falls, as the water moves back towards the sea, those are called ebb currents. And then there are times when the in between these, and that is called slack water. The areas that are covered and uncovered by these currents are called tidal flats. And these are shown at the bottom of page 476. You see these tidal flats, and you notice at high tide they're completely invisible, and then at low tide there's people, walking around on them. Tidal flats can vary from very narrow strips of land to zones that can extend a couple of kilometers. So they're not important in the open sea, but along estuaries or bays, they can be very important and create these tidal deltas. And we saw an example of a tidal delta back in this figure here. So this area here would be referred to as a tidal delta. And so this can be caused or be influenced by those ebb and flood currents. So that now is the end of chapter 15 and the end of our unit on oceans.